So let's do one more example of Dijkstra's algorithm, and let's do finding the shortest path between vertices A and G in the graph that we have here. All right, so we're going to start at G. Again, we're going to call the distance from G to G 0, and we'll work our way backwards from G to all of its adjoining vertices. So, of course, if we go backwards, the distance to E would be 7. And the distance to F would be 6. Now let's work our way backwards from F and from E. Now, our next one kind of in line here is D. And if we look at D and we think of all the pathways leading backward to D, we could have 2 more, which from this 7 would be a 9 for D, or 4 more, which would be a 10 for D. So really the shorter path is the 9. So that's the smallest amount that D could be. Now let's go back to B and C, which are kind of next when we go backwards. B, we could come in from E, which would be 6 more added to the 7, or 13. Or we could come in from D, which would be 3 more added to 9, which would be 12. And so 12 is the smaller amount. Okay, now let's go to C and see coming backward. We could come backward from F, or we could come from D. So if we came from F, we would have 6 plus 5, 11. And if we came from D, we would have 9 plus 2, 11. Both of them are the same amount. So either way, we're going to have 11 for C. And we could come either route and still have the minimum distance here. Now let's work our way back to A. All right, so A, if we come from B, it'll be 1 more, so it'll be 13. If we come from C, however, it will be 4 more, so that will make it 15. So 13 is the shortest route. All right, so let's see what our 13 would be. Let's see, we came from B, and the 12 actually came from going this direction, and the 2 actually came from going this direction. Of course, the 7 actually came here. Now, when we're listing this as an answer on a test, we'd say, okay, we want to go from A to B to D to E to G. All right, so notice we just list it by its vertices. Now, if there's more than one pathway between A and B, we would have to probably just make some sort of reference to which pathway. But we will generally not have to worry too much about that. All right, so now let's get a couple of new definitions. Euler Path. An Euler Path was invented by a famous mathematician known as Euler, and it is pronounced Euler. It looks like Euler, but it's Euler. All right, and an Euler Path is a path that uses every edge in a graph with no repeats. So we're going to use every edge. Let's suppose a postman wants to go the least amount of times down a street. So traveling just the edge once is going to be a lot easier for him than having to repeat that. So we are going to look at Euler paths. We want to travel every edge in a graph with no repeats. By the same token, an Euler circuit is a circuit that travels every single edge in the graph. All right, so let's begin though by finding an Euler path. All right, so in the graphs shown below, there's several Euler paths. So realize we could have more than one. One such path is C, A, B, D, C, B. All right, now this one's not a circuit because we're not starting in the same place and ending in the same place. It's a path. All right, but it did cover every single edge. Notice that if I were to kind of shade across that, C, A, B, D, C, B. I've covered every single edge. Now I'm going to erase those. All right, and notice also they put arrows here kind of showing the directions there. All right. So an Euler circuit is a circuit that uses every edge in a graph with no repeats, but it starts and ends in the same place. So here's a graph with a circuit. And let's notice that they've actually given us two different circuits. No, it's really not two circuits. It's just listing them in opposite order. So let's follow that circuit. So A to D to E to A to C to E to F to C to B to A. Now notice that we covered every single edge. We can visit the vertices as many times as we want to. Our goal is to only cover each edge once. So think of your postman who wants to walk as little as possible. He wants to go down the streets only one time. Okay, so that's our Euler circuit. All right, now, this is a very important idea. Euler's path and circuit theorems. A graph will contain an Euler path if it contains at most two vertices of odd degree. All right, so in other words, and this may be easier for you to think about, we are allowed to have all even vertices except for two of them. So we can have two odd vertices and it will have a path. We can have no odd vertices and it will have a path. So all even vertices or all even vertices and two odd vertices. We will never see one odd vertice with a path. So all even or all even and two odd. Now a graph will contain an Euler circuit only if all of the vertices are even. Now remember, the degree was the number of edges coming out of a vertice. So it'll have an even number of edges coming out of the vertices, all of the vertices, if it has an Euler circuit. So let's look at an example. Let me do this one. So let's notice, if we look at this, it's asking whether or not it has an Euler path and whether or not it has a Euler circuit. If we look at A, 1, 2, 3, 4 coming out of A, so that's even. B, 1, 2 coming out of B, so that's even. 1, 2, 3 coming out of D, so that's odd. Out of C, 1, 2, 3, 4, that's even. And out of E, it has one edge coming out of it, so that's odd. So we have two odd vertices, D and E. Now remember what it said up above. It will have a path, it has an Euler path, if it has all even vertices or it has even vertices and two odd. So it has an Euler path, but it does not have an Euler circuit, because an Euler circuit requires that it have all even vertices. Okay, so let's just find a path. Now, to find a path, we always, if it has odd vertices, start at one of the odd vertices. So let's find a path. So here's an Euler path. I'm going to start at the E since it has is an odd vertex, and it's going to end at the other odd. So I'm going to go here, and I'll just choose to go here. And then let's see, let's go there, and maybe there, and here, and here, and here. Notice I've covered every single edge. I started with one of the odd vertices, and I ended up on the other odd vertex. All right, and I made an Euler path. I covered every single edge. We cannot, of course, make an Euler circuit in this situation. So let's look at this one and let's determine if this has an Euler circuit. Well, let's notice this one is even. 1, 2, 3, 4. So B is even. 1, 2, 3, 4. E is even. 1, 2, that's even. 1, 2, 3, 4, even. 1, 2, 3, 4, even. 1, 2, 3, 4, even. So all of the vertices have an even degree, which means there is an Euler circuit. In fact, there's multiple Euler circuits. So let's find one of them. So I'm just gonna start at A, which means I've got to end at A. Doesn't really matter where I start though. So I'm gonna go A to B. Let's go to E. We'll just go around the outside first. To G, to F, to C. I don't want to go back to A yet because there's only that one pathway left. So let's go here, and here, and here, and here, and here, and whoops, here. I got way off there, and here. So I've covered every single edge one time. Now remember, I can go to the vertices as many times as I want. I can only cover the edges once each. Don't cover an edge twice.